Thank you for kind introduction. Hello, my name is Choi from Kyung Hee University. Title is Kinetic Chemotaxis Model from Photometric. First of all, I would like thanks for giving this good opportunity to Professor Young Kim. Actually, it's my pleasure to present in front of Professor Thomas Hillen and other great mathematicians. This is joint work with Professor Young Kim. Actually, today morning I realized that this title is a little bit scary because it contains some scary word. Kinetic, this is physics. Chemotaxis, biology. And metric, this is geometry. So this is not my major. Actually, so I think some audience think that, oh, this is so complicated. But I confirm that my talk is really simple, and I just explain some simple idea, and then I will derive some simple chemotaxis model, and then I will explain some convergence results, some between kinetic model and some diffusive model. This is some outline in my talk. In this talk, I'm going to tell you in this first stage some kinetic theory. What is kinetic theory? Just very short introduction. Next, I will explain some photometric idea, and then we can derive some simple equation, chemotaxis equation, and then for this equation, then we can find some traveling wave solution. And then finally, let me show you some discrete velocity model. This is some kind of kinetic model, as Professor Thomas Hillen explained. And then for this model, I will try to find some traveling wave solution, and then let me show you some connection between this model and this diffusive model. So the kinetic theory, actually in my PhD thesis course, my major subject is this galaxy dynamics, and so I just study about some kinetic theory. So I just choose this picture. But now I study about some microscopic cell, right? So this is so large scale, and now I need some what's that? Some microscope, right? So the main idea, main notion is phase distribution. Okay. Kinetic theory is originated by this Boltzmann, Ludwig Boltzmann. As I know, Boltzmann is German, right?
Yes.
So Boltzmann think about some kinetic theory. He invent some page distribution. Actually, I think it's new idea, but other scientists in this area, in this period, they attack Boltzmann. His idea. So eventually, Boltzmann killed himself. Actually, this is very sad story. Anyway, so Boltzmann think this page distribution. This is page distribution. Do you know? I think every audience know particle density function, right? So if we take any fixed time t and then put some position x, this PDF means some expectation or some number of particles. So main idea of this page distribution is velocity distribution like this. So we need one more variable. So x, v, t. So eventually we have 7-dimension function. So if we have this page distribution, then we have a lot of information. First of all, if we take any interval in this 6-dimensional space, like this, and then this means existence expectation. We can also obtain some macroscopic variable like this if we take integration with respect to v. Then we have this mass density and this momentum. Also, we can obtain energy and entropy. For example, if you consider some one point particle, and let me assume this point particle moves linear motion. It have linear motion like this. Then our velocity distribution have this form. Actually, the product of two Dirac delta, x here v. Okay, it's easy, right? So another example is Maxwellian distribution. This is some kind of steady state. So so this have this Gaussian distribution like this. Okay. So the kinetic theory is one of description for some dynamic consists many particles. Actually, this is PDE. So goal is to find this page distribution. The most well-known example is Boltzmann equation from Boltzmann. Here is some kind of transport term, and this is collision operator. So Boltzmann equation represents some collisional dynamics. This is collision operator. It's so complicated, right? Actually, this is simple form. We need this formula for V star, V prime, V prime star. And this is some scattering kernel. Another example is this Poisson system. If we assume there is no collision or the collision is ignored, then we can consider this Brass equation. So there is some force field. So Poisson field govern this system. Then we have this Brass Poisson system. Actually, this represents some galaxy dynamics. Okay, so why we study kinetic theory?
So I have some basic question.
Yes.
In the previous page, what phi represents?
Phi. Wait. Thank you. You mean this one? Right? Actually, this is some kind of approximation. I mean, if we have some particle and this particle have some electric field, then this system is governed Maxwell system. Then, if we take the light velocity goes to infinity, then so-called Newtonian limit, then we can obtain this Poisson system. So in this case, this one means electric potential. Yeah. And for the galaxy dynamics case, this means gravitational potential. Right. So, any question?
I have a question.
Okay, thanks.
In the previous slide,
Wait.
is the total mass assumed to be 1?
Yes. Sometimes we can assume the total mass equal 1, but actually it's necessary. It's not necessary. Yeah. If we assume this total mass equal 1, then this means one particle distribution case. Anyway, it's so any case is okay. I mean, yeah. Okay. Let's consider there is some several particle. Then this particle move, and the particle couple each other. Then we can construct some ODE to describe this dynamics. So we have Newton equation. Actually, so I mean, there is molecule in the air, right? So we can find some system of ODE, right? But usually we don't use this system to describe real air flow, right? For this air flow, we use Navier-Stokes equation. But do you know how to derive this Navier-Stokes equation? One of derivation of Navier-Stokes equation is to use conservation of mass and conservation of momentum and conservation of energy. Then we can obtain this Navier-Stokes equation. But this one, there is no concept like that, right? But the phenomena is totally same, right? So mathematicians or PhDs have interest for this connection. So kinetic theory is one of some bridge. I mean, if we take some limit, I mean the n goes to infinity, then we can obtain this kinetic theory equation, so-called BBGKY hierarchy. And from this equation, we can expand this equation for some parameter. And then we ignore the higher order term, then we can obtain this fluid equation. This is so-called hydrodynamic limit. Okay. So this is really short introduction. Okay, so this is main part. Chemotaxis and photometry. Okay, so chemotaxis is some movement of an organism, and if we have some resource or morphosis, then some microscopic organism go to there. So to describe this phenomena, we have several mathematical models. Actually, this phenomenon is really important. So bacteria need to find food, right? Without food, then this microscopic cell will die, right? Actually, this is really important because the sperm, movement of sperm is also chemotaxis, right? So this is, there was some seminal paper, the Adler's paper in 1966. Actually, this is some capillary tube, and it contains some galactose. This is some food of this E. coli. And then, if E. coli is there, then E. coli have some traveling band. So the population go there. So actually, this is really important paper. So after this work, so Professor Keller and Ziegler proposed this model, so-called Keller-Ziegler model. This is some system. So U is population density. So U is U of x, comma t, and N is food density or some morphosis. So here this one is chemosensitivity, and this phi is chemical potential, and this kappa is consumption rate. And for this model, they obtain traveling wave solution. So this is our starting point. It contains some uniform diffusion and some kind of chemotactic term. So this is our main idea. If this is some level of food density, then some kind of bacteria is located in this point, then actually this one happy, right? It have enough food, so they just hang around. I mean, the random motion. But the food density is like this. Then if the location of bacteria is 4, then this one feel starvation, right? So this feel hungry, so this one try to find food. So their speed they speed up, right? And in this case, there is satisfaction. So actually, in my case, I will take a nap, right? So their speed is so low, right? But in this situation, so we consider some geometric idea. I mean, for this one, we try to make some flat. in some geometric idea. And then this bacteria maybe have random motion in this flat space. So just consider this distribution of food, okay, the density of food, and then we can define the distance between 2 points like this. So first of all, we consider some new variable y. So y is like this. And then we have some simple formula. The metric is described this new variable, just difference between these two variables. So we have new variable, right? And just consider this relative density, because we considered the reason to consider this one is the important thing is this relative density. I mean, as I mentioned before, the bacteria will feel satisfaction or some starvation for this variable, right? So we consider this one equal V. So finally, for this y variable and this V, so this satisfies this diffusion equation, just uniform diffusion equation. So from this simple formula, we can obtain this new equation. So simply this is non-uniform diffusion equation. So time derivative of u equal 1 over m times x derivative of u of m, and this is typo.
Comma.
Oh, right. Comma. Maybe. Sorry. Yeah, thanks. And this is consumption rate. So there is no diffusion, we assume.
Sorry, I missed this. What is the typo?
No, this one. No typo, actually. This is comma. Right. So we have new equation, right? So, and from the other seminar paper, the first trial is to find traveling wave solution for this equation. So traveling wave solution means this kind of solution. This just go straight, right? And actually, it's not good example.
Is this just auto wave?
Right.
Auto wave, not chaotic.
Right. But I cannot find some good movie and good pictures. So to find traveling wave solution, first of all, we define some traveling profile like this. So we assume if some solution have this form, then we call this solution is traveling wave solution. So we have ansatz, right? So we plug this one into our previous PDE system, then we can obtain this ODE system, right? Actually, ODE is not easy to solve. But in our case, have some good structure, so we can easily solve this equation. Now we assume the boundary condition is like this. So this profile the derivative of u profile goes to 0 as this variable goes to infinity and minus infinity. M is also same. And each value have some convergence point, convergence value like this.
Sorry, one more
Okay,
question.
good.
Are those propagation speed of those two components are same?
You mean,
Yeah.
these two things?
Yeah, two things.
Yeah, sure.
We have two things.
Yeah, sure. Yeah.
So for his question, is there a possibility that two
Yeah,
different
yeah.
speed? Is that possible? That's probably
I'm not sure. How do you think of?
But it's not possible. Yeah,
Yeah.
actually you can check.
Yeah, actually good question, but I don't know.
We know. I know it's not possible.
Really? Yes, correct.
Okay.
Yeah, it's impossible. Okay, so now our goal. Oh, oops. No battery.
And then?
저기 여기 이거
The battery?
yes. I'm afraid
The
it,
battery is right on the side where the chair is.
조만간 꺼지려고 하는. 그럼 우선은 하다가 이걸 마우스로 하겠습니다. Okay. I'm sorry. So the first goal is to find the decoupled equation from this system of ODE. To find this decoupled equation, we take integration of the first equation on this interval. Then we have this one. C is some traveling speed, right? And U plus is boundary data at infinity, x equal infinity. So minus U equal minus the integration of this term, right? Sorry, here. So we have this derivative, so simply we have this one. But we assume this condition, U prime goes to 0 and M prime goes to 0. So this term equals 0. Finally, we have this one, right? Oh. Thanks. Good. Okay, so now wait a minute. Where is now we assume this U plus equals 0, then we have this one. This is assumption. So we have this one. So from the second equation, U equal C M prime over K of M. So we have this equation, right? So we take integration one more time. Then we have this term, right? So here is derivative. So we have this simple formula, right? Because U plus equals 0, so this equals this benefit. So finally, wait, this one, right? Okay, sorry. So this term equal this one. We make this simplification, right? because m prime is there, right? So by the change of variable, we have this one. Finally, we have this simple formula, right? So actually, there is no complex calculation, right? So we have u. So u is actually the function of m, right? Just function of m. So originally we have this equation. So u is function of m. So this one is just decoupled equation, like this. So if we solve this simple ODE, then we can have traveling profile. So simple page plan analysis gives some global existence. So I just skip. So finally, there is some several good property of this system. I just skip. Anyway, so this diffusive equation have traveling wave profile and traveling wave solution. Okay. Okay, actually this is the main part. Okay, I just have. Okay, so anyway, so as yesterday, the Professor Thomas Hillen explained this equation, right? So, sorry. This is diffusion equation, right? And this is some kind of discrete velocity model. And if we take 1 over epsilon and 1 over epsilon square as coefficient, then if we take epsilon goes to 0, then this one give this diffusive equation. So this is just some kind of uniform diffusion equation. So for this kinetic description, there was several results. The 2000 Thomas Hillen and Hans Osmer proposed this model, and 2004 Possam and his collaborator proposed this Boltzmann type equation, and Professor Hyung-Joo Hwang and Professor Kyung Hee and Stevens gave some result, and there are several results for this kinetic description, but I emphasize that this is some kind of Boltzmann type equation, right? So now let's in this section I'm gonna tell you this is uniform diffusion. So we have photometric idea, right? So for this process, we can move this one into some non-uniform diffusion idea. So let's consider this Broadwell type kinetic model. Okay, I mean we have this uniform diffusion equation, right? So we have change of variable, right, and photometry. Then by the same process, we can obtain this one. from the previous section. Okay. Here the U plus is population density with velocity plus s, and U minus is population density with velocity minus s. Okay. And this is running term, and this is tumble term. So S is microscopic speed, and lambda 0 is turning frequency, and K is consumption rate here. So total density is U plus plus U minus. Actually, the totally same form. So our goal is to find, our first goal is to find a traveling wave solution. But
Question.
yes,
So you said that the velocity is s, but that's not s.
sorry.
You said U plus is the population density with velocity s.
Correct.
But over there, that's not velocity. Velocity is look like s over m.
Okay. I'm sorry. I mean the innate velocity. S is some reference velocity, and real velocity is the s over m. Okay. I mean this will come from here.
So can you consider S is a velocity in some photometric?
No. I mean the simply you can choose s equal 1, and the real velocity is 1 over m of that microscopic organism. So actually this is some kind of simple convention to find traveling wave profile. We define some macroscopic variable, rho equal U plus plus U minus, and this pro J equal S over M times U plus minus U minus. From this notation, our this system become this form. Okay, so we define traveling wave profile like this, as same as the diffusive equation case. Then we have this. If we define this equal G, then we have this system of ODE, but it have good structure. The calculation is really wrong, and this is just routine calculation, so I just skip. Eventually we have this explicit formula. So capital F is here. Finally, the same as the diffusive equation case, we can obtain this decoupled equation. So the same way we can obtain the global existence. Okay, so we have traveling wave profile. But we need one more assumption here. The U plus is the boundary value. So actually this is the maximum speed or microscopic speed. Maximum microscopic speed. So our traveling wave solution is less than this maximal microscopic speed. Then we can obtain this traveling wave profile. So finally, if we assume this one is the traveling wave profile of this diffusive equation, and U epsilon is our this traveling wave profile with this epsilon coefficient 1 over epsilon and 1 over epsilon square. This is parabolic limit, right? So if we take epsilon goes to 0, then these two profile, this one converges to this profile. Actually, for the general data case, this is general case data. General initial data case is still open. Okay, thanks.